Welcome to the May 2024 Imaging SIG meeting for SJAA. And tonight we have Glenn Newell. He's going to tell us all about single board computers, microcontrollers for astronomy. Glenn, take it away.
Thank you. And this is where you click to get the mouse to move, slides to move. Okay, so we're going to talk about why this is a thing. And then we're going to get into some definitions of what is a single board computer and what is a microcontroller and a little bit of the differences, and kind of zero in on the exact hardware that I've used. And then the bulk of the thing is a little bit, overview into what you need and how you get started. But the bulk of the presentation is just examples of things that can be done that I know about because I've done them. So that's what the agenda is. So diving in, why would you want to, use a single board computer or a microcontroller for astronomy? So one reason might be cost savings, right? So rather than spending, $200 or something on a focus controller, you can probably build it for, like $50 or something, or even less, if depending on the stepper motor that you choose. It might be that the thing that you need doesn't really exist commercially, or that the things that are available commercially just don't quite fit what you want. It could just be that you love to tinker, right? So some of us, a big part of the hobby is mucking with the equipment. So we get bored if it's the same rig every day in and out, and so we like to make changes and add things and try new things. So that could be part of it. It also combines well with 3D printing. We've had presentations on 3D printing and astronomy, and I'm sure that'll continue as new materials and stuff and new printers come. But that's kind of a powerful combo, is being able to automate things with microcontrollers and 3D print your cases and your adapters and whatnots. So projects can be as simple or as complicated as you want to make them, right? So it could be something where somebody has, they've got a GitHub and a PC board you can buy, or a whole kit you can buy, and all you have to do is put it together. Or it could be that you are going from scratch and you're going to order the parts and write your own software and all of that. But there are, since we're talking about astronomy, at the end of the day, a lot of this stuff you need to talk to your imaging software. So there are people have either written ASCOM or Indy drivers for these things that we're going to talk about, or you manage to make your project compatible with an existing driver, right? So you make it look, talk, and act just like a Moonlight focuser, then you can use the Moonlight ASCOM driver as an example. A lot of this involves stepper motors and possibly servos. And, for me, I knew nothing about any of that stuff, but it didn't turn out to be that big a deal. So this is a kind of a fun way to get your feet wet in some areas maybe you didn't know anything about. And yeah, yes, it's electronics, and yes, it's software, but it's not very deep in any of that stuff. So you may find that it's easy to adapt, and certainly with AI these days, right? You could say, write me an Arduino sketch to, do whatever, and it would probably write the whole thing for you. So, but again, we'll have an example from Julian here in a minute on his focuser project that is like a shining example of something where it's all the engineering is done and you can just buy it and put it together. So what's the difference between a microcontroller and a single board computer? So I'm going to talk about, Arduino microcontrollers, and mainly the Uno and the Nano, which are kind of the original from Arduino.org themselves. There's clones and other things, but that's mainly what we're going to talk about. And then on the single board computer side, we're going to talk about the Raspberry Pi. And even within the Raspberry Pi, the current state of the hardware, a Pi 4 or a Pi 5, if you're going to use it for a full-on imaging computer, or if you're doing something smaller, maybe a Pi 0 2W, which means it has Wi-Fi. So I won't read through all of the bullets here, but on the microcontroller side, basically the last bullet you could think about, this is the kind of level of thing that would run like your electric toothbrush or a coffee maker or something, where it's low complexity software controlling some motors and maybe in the case of the coffee maker, a heater and a valve or two. Right, so it's not super complex stuff, and therefore there you see the 8-bit architecture there, and small RAM size and slow processing speed, all of that. So to kind of compare and contrast on the Raspberry Pi side, especially with the Pi 5, they're getting quite respectable in terms of the performance. There's 64-bit now, at least the Pi 4 and the Pi 5. And you can have up to 8 gigs of RAM, and they're getting pretty fast, and it runs Linux. So it's almost a full-on. Certainly can be a desktop. You can have a Pi 5 or Pi 4 with 2 4K monitors and all of that. So they're pretty respectable these days. So that's kind of the difference between the two here. So these is a sort of random list of stuff that I have built using single board computers or microcontrollers, and I've broken it up into the Arduino based stuff in the cyan color there, and the Raspberry Pi stuff in the magenta, right? So we'll talk about different focusers I've done, and flat panel control, and flip mirror, and various environmental controls, and a rotator for my main rig, and particle sensor. This was when we had a lot of wildfires and smoke in the Bay Area. Paulo and I both built these particle sensors, and then we can look and see if it makes any sense to image or not based on the particle count in the air. And then on the Raspberry Pi side, certainly, you can use it as your complete imaging control solution, whether you roll your own with K-stars, or you buy a StellarMate or ZWO ASI Air. This kind of a closed box, but it's actually a Raspberry Pi underneath. That's possible. Some other things I've done, all sky cameras, and now I've added a second instance of running the all sky software with a camera pointed at my telescope, and that way I can look out in the yard and see where my telescope is pointing, and also get a time lapse the next day of what the telescope did while I slept. And then straying a little bit from the core astronomy stuff, I've been working on a project for SJAA where, you know, there's a lot of people now that have C-stars or other electronic assisted astronomy all-in-one scopes, right? And these are great tools for public outreach, but they often, you know, you have to join the Wi-Fi at the scope, and you have to either share control or you have to have some software ahead of time, like the application, in order to see what the operator is doing on your device. And so there's a project to instead just join a network with a QR code, and then as you go to each telescope, you can get the stream, and that's all done with Raspberry Pis. And straying even further from, I threw in a couple extra things, right? So again, the tie-in between 3D printing and astronomy. So you can have an Octoprint or Octopi, you know, print server for your 3D printer. And then I think I even threw in one more Pi project that when I got my Pi 5 and then for fun added a NVMe SSD to it, then it was suddenly, you know, like a server class machine almost, and I needed something to do with it. So I'm running a Pi-hole, which is your whole home network DNS solution, which then becomes an ad blocker and also blocks, you know, questionable servers and whatnot from you being able to get to them through DNS. So I've got one or two slides on that. So let's dive in. A little more detail on the Raspberry Pi. Again, it's an ARM-based single board computer running Linux, although probably before too long you'll be able to run Windows on it too, I would imagine. But again, it could be your entire imaging computer, similar to an ASI Air or a Stellarmate, or you could just use it for a single function like an all-sky camera. I think these days, like I mentioned, I've talked through most of this already, but you know, Pi 5 or Pi 4B, or even the Pi 0 2W are probably the hardware choices. There's more models and older models, but those are the current and probably the most applicable ones. And again, you can buy these as a complete kit, shown below there for the Pi 0 2W on the left, and I think that's a Pi 5 on the right. You can buy a complete kit with kind of everything, and you just put it together, or you could buy them a piece at a time. You know, the Pi hardware itself, the case, the fan, the power supply, the SD card. So your choice on that. And you need a way to get the operating system onto the SD card. The SD card is what the Pi uses for its storage, unless you add an add-on board to it for an SSD or something. So as part of the ecosystem, Raspberry Pi has this Imager software, and that makes it a pretty easy, you know, 3-step process. And I show here on the right, you know, one possible SD card to USB adapter. It's kind of clever that actually fits inside the USB connector itself. The SD card slides in there, and then you just plug it in. And so you just, in software, you just choose what kind of hardware you have and what operating system you want to put on it, and then, you know, pick the storage that you're going to write it to, and away you go. So that's a pretty simple process. I've tried other more generic writers, but they always seem to be a little problematic, and this is just very convenient because it has the images all, the process of downloading and installing the image all combined in the one piece of software. So you can certainly, run we'll call it a headless Pi, right, with no keyboard or monitor or anything connected. But there's a bit of a chicken and egg situation, right, where at least for troubleshooting or for getting it initially set up, you might want to plan on having a way to plug it into a monitor and a keyboard and mouse. As part of the imaging process we talked about on the previous page, you can set up the network and some other things, like the configuring, SSH and VNC as part of that imaging process. But if something goes wrong, then you still need a way to kind of troubleshoot, and being able to get in there with a keyboard and monitor is a good way to do that if you can't access it via the network. Okay, so just the three different models that I talked about. The Pi Zero, is I use that for an Octopi 3D print server with a camera connected, and I use it with running an instance of the All Sky camera, again with a camera connected, pointing at my telescope in the yard. So it's kind of just enough hardware to do that. There's a unique thing there, the USB 2.0, where it says OTG. That's a combination kind of in and out in one port. So you need a special cable to then treat that like a regular in and out port. Let's see what else. So then on the left down here, we have a Pi 4 and then the Pi 5 on the right. And they both use the micro HDMI connectors for monitors, and they both use USB-C power jacks, but the Pi 5 has a higher power supply need. You need a 27 watt or a 30 watt power supply for the Pi 5 versus the Pi 4 is less than that. Okay. Speaking of power, so how do the Pis are, 5 volt. So how do you deal with that in the field? So this is one little bit that I found that's convenient. So you can plug in your 12 volts there, and it gives you two 30 watt USB charging connectors that you can use to power your Pis. So that's good. All right, so diving into some examples. So, hi, this is your rig circa
Yeah, a few
20
years.
something, few years back, right? So you see there the Raspberry Pi 4 in a metal case with his running his whole rig there with K-stars.
And there's definitely a 12 volt to 5 volt converter somewhere in there
Somewhere in there, yeah.
because it had a 12 volt power supply that you could sort of see the tip of on the bottom.
Yeah, you see the Anderson power poles there, yeah. So again, you can run a K-stars, which is kind of an all-in-one imaging, open source imaging software, and Hi has contributed a lot of features to that. So I think he's highlighting some of those there in that screenshot. So there's that, and then of course we mentioned that you can buy something already put together from StellarMate or less open source is like a ZWO ASI Air is the same, pretty much same form factor. That's a Raspberry Pi underneath. Okay. Jump into the all sky cameras here. So again, I've put URLs for the relevant bits on all these projects. And of course, there are multiples that you could choose on any of these things, right? So these are just the ones that I settled on. So I think I'm on my third rev of this guy's all sky camera, as I've melted various ones of them before adding fans and whatnot. So this is just an example. I have a monochrome camera. So there's a daytime shot of some pretty clouds. And here on the left, we have what the web page looks like. So it's on the public internet. And as I mentioned, now I have two instances running. So in the top is obviously the all sky camera, and then I have another one that's pointed at my telescope in the yard there. And then on the right hand side, you can see the sun bleached ZWO red camera pointing up and with a temperature probe there. And then the Raspberry Pi 02W with a camera, with the Raspberry Pi camera module pointing at the telescope. And I have more work to do on that because this is when it rains, it fogs up. So I'm going to have to put it in a different case. But so now we're jumping on to the streaming server. I'll go really fast over this because it's sort of only semi-relevant, right? So two or three pieces of hardware put together and a couple pieces of software to make this thing. And so maybe even start here. I mean, this is what the public sees, is this sign, right? So the idea is that each C star or what have you would have one of these signs lit up dimly at the star party. And so you walk up and you use the top QR code to join the public Wi-Fi that SJAA provides. And then that's the same for all the stations. And then each station, we call it, each scope would have its own streamer. And so that's the second QR code. So once you're on the Wi-Fi, then you can launch the stream, and it doesn't require anything to be installed on the phone or the tablet, right? It just uses the web browser basically to do the playback. And then on the back side of the sign, you can see the bits that went together to make this, right? So there's a battery and a switch and a Pi 4, and there's a device that handles all the different types of screen mirroring that you could do based on what the operator of the telescope is using. And then that can also be deleted if they're going to use a cable instead of going wirelessly for their screen sharing. Yeah, and then Wolf in the solar program is also going to use these, and so he is making a cleaner setup with 3D printed mount for all this stuff on the back of the sign. So this is what that looks like. So this will last for 4 or 5 hours, which is plenty long for a public outreach star party.
And you have one for each telescope?
Yeah, yep. Okay, moving on, then Octoprint is, a 3D print server that gives you a camera to look at your printer when you're away from it and look at, so you can troubleshoot issues or stop and start prints. And it also gives you the time-lapse capability and it eliminates the need to move an SD card between the computer where you're doing the slicing and the printer, right? So it's nice because it's one of the things that kind of surprised me about 3D printing. You think of a printer as being something that's on the network and you can print to it from your computer, but most of the 3D printers, you have to move an SD card. So this eliminates all of that. So on the left here, we have an example of what that user interface looks like. And there's a number of tabs here that you can, see the printer, see the G code, see the temperatures, all of that stuff. And then on the right, this is the Raspberry Pi 02W. You can see the little heat sink sticking up here in the back, and a camera module. This one happens to have infrared LEDs on it as well. But this is what I use on my Delta printer to drive that. And then kind of an interesting little, again, USB bit is you can see this semi-transparent piece here on the USB cable that's going from the Pi to the printer. You need to actually block the power from flowing from the Pi. You want the data to flow, but you want to block the power so you're not trying to backfeed and power up your whole printer from the tiny 5-volt supply in the Raspberry Pi. So that was something I didn't know about, and it's a whole $8 piece of stuff, or you could build one, I guess. And then lastly, on the Raspberry Pi side, I've talked about this Pi-hole software. So it means that everything in my house now is got its, all the ads are blocked, and there's some amount of protection from malicious websites and other things as a result of that. And I wanted that to be pretty beefy, or actually I built something beefy first and then decided I needed an application for it. So again, the Pi 5 with the active cooler and the spelling error here, NVMe, I missed the M, based with a 500 gigabyte SSD. And that looks like this. The web-based UI is on the right there. And you can see, if you turn the thing over, you can see the NVMe base that I chose to use. So it's a circuit board that connects up to the Raspberry Pi. And this one's from a company called Pimoroni. And then this is what it looks like on the top side below here with the active cooler. Okay. Any questions about Pi before we move on to microcontrollers?
I just comment that when I was messing with the Pis on my astronomy rig, I just moved over to, SSDs and skipped the SD card. And in fact, the way I remember it, hopefully not wrong, you don't ever need an SSD card. Like you could bring up you can write using that same Raspberry Pi software, the OS onto your SSD, and then just plug in your SSD into the USB 3 plug, and it boots straight from that. And I don't think you need an SSD card in the equation if you don't want one.
Well, yeah, this is something that's just new on the Pi 5, is this NVMe interface.
No, I
right?
meant, yeah. So I meant this is all with Pi 4s.
Yeah,
I haven't had a Pi 5, but with the Pi 4, you could, plug
yeah,
it to the USB and
yeah.
we're good.
This was to go, and again, it's probably overkill for what I'm using it for, but it was just kind of interesting to see how big a beast you could make with the Pi 5. So I went for the
All right.
NVMe. base there. Yeah. Okay, let's move on to Arduino microcontrollers. So there's the URL for the main website for the actual Arduino hardware and software. So, you know, there's lots of different models there as well, but the ones that I've used are either the Nano on the left or the Uno on the right. And they're essentially the same kind of from a software standpoint, and it's just really the form factor that's different. They're powered just by plugging them into a USB from your computer, and that's also how you talk to them. It makes a serial connection over the USB, and you know, you can have a larger power supply if needed. But yeah, the USB is typically enough. And then there's breakouts and what they call shields, right? So shields are boards mainly for the Uno form factor that just sort of pile on top, kind of like you saw the base board for the Raspberry Pi, these sandwiched together. So this example on the right is something that's got the capability of driving, you know, motors from the Arduino. So those types of things are available if you don't want to do more, you know, breadboarding and building your own circuits or whatnot. And then also these breakout boxes or breakout tools or whatever you want to call them, breakout boards, I guess, on the left here, enable you to do things without having to solder, right? So a lot of the projects that I've done are using these breakout boards. So Arduino, you need to program, and it's programmed with something called a sketch, and it's pretty much C language, but don't let that scare you off if you're not a C programmer. Again, especially in these days with AI. But if you go through, you know, some of the examples, it starts with, you know, let's make an LED blink or something, right? Then it's a kind of a step-by-step process. You can learn how things work, and also, you know, there's libraries. So on the right here is part of a sketch I've written for, you know, doing dew heaters and turning fans on and off based on ambient temperature versus, you know, another temperature type of thing. So I don't have to write the part that you know actually reads the temperature from the sensors, right? That's in a library, right? So you can see here this sensors get temp. Sorry. Right, so there's a library for that matches the hardware, the sensors that I bought, and you know all of that is open source. So basically, you connect your Arduino via USB cable, and then you go in there and in the IDE, you select what your hardware is and then what serial port it's on, which is going to be a virtual serial port over USB. And then you can compile and upload. And also, I should have written here, you can also monitor if you put in serial, if you put in print commands or what have you, you can also get data back over that interface if you need to. Okay, so then let's dive into some projects. So again, shout out to Julian here. So here's an example of a super well done, you know, project where the software is on a GitHub, and he's made the PC board you can buy, and takes you through the whole project. So if you need a focuser for your off-axis guider, this might be a really good project to get your feet wet with Arduinos. So for me, several years back, Paulo and I both were looking at doing some wide field imaging with camera lenses, and we needed a way to focus. So he educated me some on stepper motors, and so we started working with stepper motors and 3D printed gears so that we could turn the focus ring of a lens. And then again, there are Arduino sketches that are available that do that software piece and also make it look like a moonlight focuser on the serial side so that you can use the moonlight drivers for that. I will note that in this case, somebody came up with a better mousetrap. And so for Canon lenses, this company, Astromechanics, they have an ASCOM driver and kind of a shim. You know, it's a Canon EOS male and female in a short body. You put the lens on and then you put it in your camera, or mount it to your Astro camera. And then with an ASCOM driver, a USB connection, you can control the focus motor in the lens itself. And so that's a cleaner solution. And so that's what we moved on to. But this is just an example of, you know, if you had a non-Canon lens or something that you needed to do, this would still be a legit way to do that. You know, I've built several focusers for different telescopes. This is one for a Mac CAS, and it's, you know, down inside this 3D printed holder here, which holds the motor without modifying the back end of the scope. You know, there's a 3D printed piece that fits over the focus knob and tightens down. And so that's how that works. And you know, you can get a kit of 5 of these motors and 5 of these little controller boards for probably less than 20 bucks. I think they're like $5 a piece, so it's really inexpensive. The only downside of this size motor is it doesn't have a lot of torque, right? So you might need a bigger stepper motor if you need more torque than that. So speaking of which, here you can see on my Coronado PST, I've got 2 different stepper motors here, and one you can see more on the bottom left. I'm using it to turn the focuser knob on the back of the Coronado PST. And again, all this is without modifying the PST at all, using the existing mounting holes and whatnot and 3D printed brackets. And then I also wanted to be able to control the Edelon tuning remotely. So that's the second one here. So we've got, and they're both show up as, you know, moonlight focusers. So by using the focus driver inside sharp cap in this case, you know, to focus, and then a standalone moonlight focus application to control the Edelon tuning, is how I do that. Okay. Another project I did was to make a flip mirror that I could control remotely. And this came up both in terms of planetary, and when I was goofing around with some spectroscopy, I wanted to have one camera that had, you know, kind of a wider field view, because one of the big challenges with planetary is just getting on the target. And so the idea here was to use a flip mirror to flip between a camera that's before the Barlow in the case of planetary, or before the spectroscopy spectroscope grid in the case of spectroscopy, and the rest of the optical train. So and to make that work, let me jump to this one here. There's a couple micro switches. So I printed a 3D printed knob here that is glued to the knob of the flip mirror, and it has a pointer on it, and the pointer is used for run limit with these micro switches, right? So it'll turn until it gets to the next micro switch, and then it'll reverse directions when you tell it to flip again. It'll reverse direction and go back the other way until it hits the first switch. And so there's a close-up of the beautifully laid out wiring mess on the right here. But so there's a sort of a prototyping board in red, and then there's a power supply board that's taking the 12 volts and giving me 5 volts. There in blue, and then this is the motor driver board that we talked about, and then in blue over here we have a Arduino Nano to run the whole thing. And then there's, I guess you kind of can't see it, but behind this cable here, there's also a push button so that you can manually trigger it when you're out at the telescope. Okay, another project, flat panels. So again, we're gonna use an existing ASCOM driver for a commercial product. This I don't know how to pronounce it, Alinitac flat panel. So we'll use that API sort of between the telescope and the hardware. And then we can just use these, they call them, sketch light box or sketch panels. And I've got a couple different sizes here for different telescopes. And these come with a built-in dimmer. And what you do is you actually just cut that out of the circuit and just put a plug in that powers the LEDs directly. And then it just takes an Arduino and a single MOSFET to do the pulse width modulation dimming of the thing and the serial communication with the driver. So now your Nina or your K-stars or what have you, can automate your flats by dimming the panel as needed. Okay, another project. So this same circuit I've used inside the all-sky camera that's on the roof to kind of turn fans on and off and dew heater on and off, and then also on my main rig, the 12-inch RC, it's controlling the dew strips for the primary and the secondary. And so in that case, there's 3 temperature sensors, one for each dew heater zone, and I try to get that as close to the mirrors as I can, and then an ambient, one for ambient temperature. So here I'm breadboarding. This is the one with the fans for the all-sky camera, and you can see these little boards that are the high power MOSFET to drive your hardware, in this case the fans. And again, these these temperature sensors that match the library of code that I'm using in the Arduino sketch. And you can see here the breakout board. So you just plug the Arduino Nano into the breakout board, and then you can use these project wires to connect things together without doing pretty much any soldering. And this is that same concept with more channels. This is for the dew heater controller on my RC. So here you can see the temperature sensors. I think they came 4 or 5 in a kit. And then this is a 4-channel controller, of which I'm using 3 of them, or 2 of them, I guess. Yeah. Not sure why I have 4 now that I think about it, but anyway. So here's just again, the IDE running, and one of the functions of the IDE here at the bottom is, you can monitor the serial output. So I'm doing some, printing some debug information, which then you can also use a serial plotter. So in the upper left here, we're seeing, the ambient temperature versus the temperature of the dew heater zones as I'm getting ready to image there. Okay. You can also, create a whole observatory control system, which involves weather sensors, and you could use it to open a roof and rotate, a slit and all these types of things. And there's, one gentleman that has worked for multiple years on that project. And so this is what the software interface looks like. And you can roll your own hardware, or he's got a board you can buy. You can see here on the lower left, and so again, the Arduino is plugged in here, and so I was interested in this mainly for the weather part of it, and then I thought, if I ever do build a roll-off roof or something, then I'll be ready to go. So here I'm just breadboarding some of the sensors. You can see on the lower left breadboard here a luminosity sensor, and over on the right is a sensor that can measure wind speed without having the anemometer, those spinning, it's no moving parts wind measurement, although I did have issues with that being reliable hardware. And I forget what this sensor here is on the lower right. I think that might be an IR sensor. So basically, you've got, is it light or dark out? Is it windy? Is it humid? What's the temperature inside the observatory? What's the temperature outside the observatory? What's the pressure? What are the sky conditions in terms of clouds? Using an IR sensor pointed at the sky. So all of those can talk back to the Arduino and then be controlled with this OSC software, Observatory Control System software. Okay. Another project I did was a rotator for my rigs. I do use Moonlight focusers, and Moonlight focusers do have an ability to rotate as part of their hardware. And there is you can buy a rotator adapter for those, but I decided to roll my own, save some money. So it's kind of hard to see buried here, but this big number one is there's a big 3D printed gear that is press fit over the where the focuser attaches to the OTA, and then the motor is attached. And I probably got another shot here in a minute, but the motor is then attached to the optical train, and it moves by that belt that you see there. It moves the whole optical train back and forth around the connection to the OTA.
Glenn, so
Yeah.
does it keep it still enough when it's not moving?
Yes.
Okay, thanks.
Yeah, well, that's kind of the whole, there's this massive dovetail with three not set screws, but three screws plus a lock screw that fit into the dovetail that make that a smooth rotating and not wiggly mechanical interface.
Yeah, no, I understand that it can rotate. I assume that you don't use the lock screw, right? Because you want to be able to.
Usually uh, it's a little tight, just like all the set screws are a little tight, just so that there's no play in terms of left, right, up, down, right? So that it can only rotate. It can't move in any other direction. And that's just a feature of, I think a lot of focusers probably have the ability to rotate, but this is already set up for, like here I'm using the stepper motor is actually mounted to the focuser using the mount screws that were intended for, their solution.
Oh,
So
I
that's
got.
how it attaches. Yeah, and then there's a belt. It's not shown in this picture, but there's a timing belt then that goes between this little gear on the stepper motor and the big gear that's press fit on the telescope. And then again, thanks to Paulo for helping me with this project. Again, we have a power supply and a driver board for the stepper motor and the Arduino there on this breadboard. And in this case, there was, somebody wrote the ASCOM drivers specifically for this project. And the thing that's nice about this is, both PhD2 and your imaging program connect to this rotator. So not only does the imaging program rotate your camera into the position you want it to be in for each different target over the night, but PhD2 then is monitoring that rotation angle and corrects the calibration so that you don't have to calibrate for each target, right? So you can rotate your camera around as much as you want without having to recalibrate. So that's really nice. And again, a lot of this has to do with that I'm using an ONAG, right? So, I don't have to worry about finding guide stars or anything as a result of rotating stuff around. So, okay. And then I mentioned the particle sensor back when we had a bunch of smoke in the air. So there's a project here where you're sort of crowdsourcing particle, pollution data, and they do whatever they need to with that. But our purpose was to know when there was too much smoke in the air, and we sort of determined that if you've got more than 10 micrograms per meter cubed, you don't want to be imaging. So this thing has been, I guess these sensors wear out over time, but it's been out there for, I think, maybe 3-4 years now. And I just, every once in a while, I get an email from them saying, hey, sensor XYZ is offline. And I just go out there and unplug the power supply and plug it back in, and it comes back up. So this is a little different board, a microcontroller with Wi-Fi built in as well. So it's got a full network stack on it. And so this is the whole thing right here, the whole project. And let's see, do I have a picture? No. You just slide this whole thing into a plastic bottle with there's a hose that plugs on right here, and you stick the hose out the part where you pour water out of the bottle, and you cut the other end off, and to slide all this stuff in there, and then you can close up that end if you need to. But that's the whole project. They have the software and everything to download and upload it to the microcontroller. So that was a fun little project. Okay, and that went a lot faster than I I thought it would. So open for questions.
Well, that was great, Glenn. Thank you. Okay, so anybody have questions for Glenn? Well, I'll start off with one comment. So I put together, back in the day when we had a lot of forest fires
Mm-hmm.
before all this rain, I also put together a air sensor, and I found a board that basically connected to USB.
Mm.
So it just became another peripheral on my Raspberry Pi. I guess if you didn't have a
Cool.
Raspberry Pi lying around doing other things, that wouldn't be useful. But in my case, it was. So
Yeah.
I just wrote a little Python script to sample it and upload it to a little web page.
Yeah. Well, there's all kinds of sensors, and there's companies like Adafruit and others that make this all possible with parts for robotics and various sensors for weather and motion
Yeah, I
and
think in the case of these sensors, what we have to thank is the lousy air in Beijing.
mm,
And, because of that, there were all sorts of Chinese air sensors made, 10 years, 20 years before our wildfires. And so there's just a glut of really cheap these air sensors. And with respect to how long they last, when I was doing this project, it was spec'd in so many samples, basically how often you sample the air. Let's say it was 10,
mm-hmm.
I'm inventing this number, but let's say it was 10,000. It was spec'd for, to last 10,000 samples. So if you sample the air every, 10 seconds versus every 100 seconds, you could get your sensor to live, a tenth as long or 10 times longer. And,
Yeah, I seem to remember something about that as part of this was they were slowing it down.
yeah, so it seemed like,
Yeah.
I don't, you don't really need to sample the air every minute, every 10 minutes was fine. And so,
Yep.
it could last 10. I remember that mine was supposed to last at least 10 years given that.
Yeah, so this Grafana interface that they have here, right? They they have various different time periods where they plot your data. So I think it's like 15 minutes, I think, is the finest resolution that you can go to.
Yeah, and then it'll probably last a decade.
Yeah.
Hey, do you guys know if either of those particulate sizes like correspond to allergens, or is this only like air pollution?
I don't.
Those are definitely the two sizes that also Purple Air uses.
I see.
Yeah.
So
Any-
probably not the right guys.
Hey, I have a comment.
Yep.
First of all, thank you, Glenn, for putting together this great presentation. It was very
Sure.
well. And thank you for the kind words as well. One quick comment, and then I wanted to get your opinion. So I think one of the, you mentioned early on in your presentation that one of the reasons why doing these kind of projects can be really interesting is when you build something that just doesn't exist commercially.
Mhm.
And so it always made me think that most equipment that you can purchase for astronomy requires wired connections, right? So USB and sometimes even power.
Mhm.
And there's, so you didn't talk too much about power consumption, especially on the microcontroller side, but it kind of made me think that I think there's a lot of opportunities to build wireless devices which use either Wi-Fi or Bluetooth or Zigbee or other, fancier protocols, and just basically like clean up the mess, the cabling mess that we all have to deal with. So I don't know. I just wanted to get your opinion on this.
Well, I have had my share of difficulties with USB, and in the beginning I was imaging with like a 50-foot, active USB cable, and then I learned the hard way about the differences in ground potential between your house and your yard and things like that, and blew up my fair share of those long cables by not having good taking care of that ground potential difference. And yeah, USB, was never intended to be an outside thing, and it just sort of barely works for astronomy, right? I routinely have to go out and slop some magic goo on my USB connectors when they've been out in the weather for a month or something, and I haven't used them. So there's definitely, something better than USB would be good. I'm a little leery about depending on like Bluetooth. Bluetooth to me is a technology that kind of sort of sometimes maybe works, but maybe it's better as each new rev comes along. But yeah, certainly, now there's, as things consolidate into like a C-star kind of thing where it's all just one, all the hardware is internally connected and you just control it via Wi-Fi. Again, they tend to kind of not pay attention to the RF part of it, right? Like some of the, the ASI Air I have, still has an internal antenna in a metal box. Not a good plan, right? So the range is very, very limited. But yeah, I mean, done right, sure, that makes sense.
By the way, the ASI Air is my understanding of. I don't own one, but my understanding is that it's basically a Raspberry Pi.
Yeah, that's my understanding as well.
Raspberry Pi with open source software, and ZW kind of polished it a little bit by making it, customized to their equipment. They're violating a bunch of open source licenses.
It can be controversial. Yeah. Yep. So I won't get into that, but yeah. Different software rules in different countries.
No, not really. If you want to sell in the United States, you have to abide by US laws, and they're violating US laws, which is why I just my personal opinion, I always tell people don't buy an ASI Air.
Yeah.
There's a lot of other options out there.
Yep. All right. Well, do we have other questions for Glenn? All right. Well, thank you, Glenn.
You're welcome.
I don't have a question, but I do want to congratulate Glenn on a great presentation.
Thank you.
Absolutely. clearly been busy the last few years or the last 10 years or whatever that represents. That's a
Yeah,
lot of
very,
Yeah, well, there-
very interesting. Quite an accomplishment.
There was
Quite a
a,
list of accomplishments.
yeah, thank you. There was a year plus space where I was not working, which that's kickstarted the 3D printing projects and the electronics projects. So that gave me some space to dive in on some of that stuff. But yeah, yeah, there's been quite a lot of different projects. It's fun.
All right. All right. Well, thanks very much. A reminder that next month, Rich Klein is organizing a talk on the solar eclipse and people's experiences. And if you're interested in contributing to his presentation, he was soliciting, it's in last month's meeting, he was soliciting, people to give him some slides. So send a note on the email, Imaging SIG email list if you're interested and don't remember or hadn't heard that. Otherwise, thank you very much, Glenn. Really appreciate it. Please unmute and give Glenn a hand, and we'll see everybody in June.
Thank you, Glenn.
Thanks all.
Thanks, Glenn.
See ya.
All right. See ya.
Thanks.